Hello everyone. Today we're going to take our study of vectors, quantities having both a magnitude and a direction, from 2 dimensions into 3 dimensions. Yes, in APC, that is one of the things that we do, is we can do all the stuff we've done before, but in 3 dimensions. And because we're going to be in 3 dimensions, we need kind of a new naming system, a new way of describing things in 3 dimensions. And classically, we use what are called unit vectors. Okay, a unit vector. So a unit vector is a vector that has a magnitude of 1. Get it? It's called a unit vector because it is 1 unit long. And if it was a displacement vector, it might be 1 meter long. If it was a force vector, it would be 1 newton long. If it was a velocity vector, it would be 1 meter per second long. Right? So it's one unit long. And because it's 1, the only purpose of a unit vector is to indicate direction. Right? It just indicates direction for us because of a magnitude being 1. When you multiply, that doesn't change anything. Now, in 3 dimensions, there are 3 unit vectors that are traditionally used. I cap, J cap, and K cap. You call these little accent things on here, right? Caps, if you will. So that's I cap, J cap, and K cap. And we tend to use, in this class, what's known as a right-handed coordinate system. Right-handed coordinate system. In a right-handed coordinate system, in which X is the horizontal axis, Y is the vertical axis, and Z is the in and out axis. Can you see that? Can you make that 3 dimensions, right, in your mind? All right, Z is in and out, X is horizontal, Y is vertical. Well, I cap is a unit vector of length 1 that is parallel to the x-axis. Positive I cap is parallel to the right. Negative I cap is to the left. J cap is parallel to the y-axis. Positive J cap is up, negative J cap would be down. And K cap is parallel to the z-axis. It is in and out of the screen. Positive K cap is out of the screen. Negative K cap is into the screen. You with me? All right, so X, Y, Z, I, J, K. Notice how they're organized alphabetically, right? I think that's clever. X, Y, Z, I, J, K, to help you remember. I goes in the X, J in the Y, K in the Z. Right-handed coordinate system. There are left-handed coordinate systems and other ones, but we're going to stick with right-handed coordinate systems in here. Now, here is a vector we will call A, which is kind of off in 3 dimensions. Really helps, if you're going to draw this, really helps if you put a little box around it, right? A rectangular box around it. Really helped me if I was drawing it by hand. Maybe think of this origin here as being the bottom corner, right, of a room. So think of a bottom corner of a rectangular room. And we have a vector that is running from the bottom corner here to the upper corner there. Okay, and that is the vector A. Okay? Now, in 2 dimensions, we can resolve a 2-dimensional vector into its 2 perpendicular components, X and Y. Right? Well, we can do a similar thing for a 3-dimensional vector, except now it will have 3 perpendicular components. So here is A sub X. This is the portion of A which is along the x-axis. If you want to be technical, this is the projection of A onto the x-axis. Here is A sub Z, the projection of A onto the z-axis. Notice they are at right angles to one another. And personally, in this picture, it helps if you draw the little right angle thing and you make them parallel to the axes. See how I did that one? See? Parallel. And then that's A sub Y, right, which is perpendicular to both X and Z. Right? All 3 of these vectors are perpendicular to one another. Notice head to tail, head to tail. And of course, head-to-tail vector construction is vector addition. Right? So just like we used to break up two-dimensional vectors into an x and a y component, we can break up a three-dimensional vector into x, y, and z components. And when we write that out, it's going to look like this. Vector A can be written as ax I cap plus ay j cap plus az k cap. Notice the ax, the ay, and the az do not have arrows on them because the direction is inside of the unit vector. This is known as unit vector notation. Unit vector notation. So this is the vector A written in 3 dimensions. Ax I cap plus ay j cap plus az k cap. Ax I cap, ay j cap, and az k cap are called the vector components of A. Right? They're vector components because they have both a magnitude and a direction. Right? Where the magnitude is the ax, ay, az, and the direction is the I cap, j cap, k cap. And ax, ay, and az are scalar components. Right? They're just sizes. They're just magnitudes. Let's take a second again. Check this out. Right? Unit vector notation. And by the way, you always write it in this order, I, j, k. All right, just to keep it consistent. Doesn't mean you can't change the order. Remember that vector addition is, after all, commutative, right, as we proved last year. But it's just traditional to write it as I, j, k, and write it in that order. Okay. Now, in 2 dimensions, we know how to find the magnitude of the vector from the components. Right? Little Pythagorean theorem. How do we do that in 3 dimensions? So a little proof here for you. Okay? Consider the vector A. The projection of A onto the xz plane would look like that. I'm going to call that little c for now. Let me say that again. Little c is the projection of vector A onto the xz plane. The projection of vector A onto the xz plane. X and z, the xz plane would be like the floor of the room, right? So if you project down through the vector, right, this is what it would look like there. Do you see a right triangle? I see one. See one there? Right? There's a right angle right there. So C is the hypotenuse of a right triangle with legs of AX and AZ. So of course from the Pythagorean theorem, C squared is the sum of AX squared plus AZ squared. Or C is the square root of the sum of the lengths of the squares of the lengths of the sides. Right? So we can put that right here. That's not the only right triangle in the diagram. Do you see another one? Don't forget, that's also a right angle. Right? AY is perpendicular to both X and Z. These are perpendicular components. So there is a right triangle here. With A as the hypotenuse, this is one leg, and AY is the other leg. So again, by using the two-dimensional Pythagorean theorem, A squared has to be the square of this side, this, plus the square of AY, sorry. But the square of a square root is just what's inside. So A squared is AX squared plus AZ squared plus AY squared. And as this is just a scalar, right, addition is commutative, and I can flip the order. And look at that. So the length of A squared is equal to the sum of the squares of the lengths of the perpendicular components. Again, the length of vector A squared is equal to the sum of the squares of the lengths of the perpendicular components. Essentially, this is a three-dimensional Pythagorean theorem. As long as the three components are perpendicular. And now that we've done this proof, you don't have to do it again. You can just use this idea. All right, just like if you once proved the Pythagorean theorem, I hope, sometime in math class, all right, you can just use it now. Same thing here. We just did a little math proof. Note that this math proof only works if AX, AY, and AZ are all perpendicular to one another, so that we can make right triangles. So this is a handy thing to remember when using three-dimensional vectors. By the way, there is another notation we could use. We technically could use two different angles to describe this. We could use the angle here in the XZ plane, and then the angle here, right? In this plane, really. And we could use both of those angles to describe where A is, but unit vector notation is just a little handier once you get used to it. And we will learn how to do vector addition, and when it comes time for it, vector multiplication with unit vectors as well as we go throughout the year. So let's do a little two-dimensional problem, because I've never really seen them ask you this in 3 dimensions. And we'll break it up into basically its perpendicular components so that we can write it in unit vector notation. Two-dimensional unit vector notation, but still. So we're going to have a vector that's 100 meters at 40.0 degrees south of east. So if you remember how to resolve the vector into its perpendicular components, step 1 is draw the vector, or at least sketch it. As always in PowerPoints, my vectors are drawn to an internal scale. Right, so there's 40 degrees south of east and 100 meters. The next step was always draw the horizontal component from the tail of the resultant. Right, so I have to draw to the right. Note, these are arrows, right, not line segments. Hopefully, as you've been doing your packets, you've been drawing arrows and not lines, right? These are vectors. This isn't geometry, this is vector algebra. And then you draw your y component from the head of the horizontal component. So this is a displacement, so I would call that d. This is d sub x, this is d sub y. Now, if you remember, in order to find these, okay, we can use the 40-degree angle. But in 2 dimensions, when we're doing positives and negatives, we either have to get that by looking at the diagram, by realizing that we're in the 4th quadrant, or the calculator will tell us, if we want to get a little more mathematically sophisticated, if we use the angle from 0, right, in our calculator, that will tell the calculator which quadrant we're in. The calculator will then spit out the positive and negatives. Do remember, though, you have to draw the horizontal component first, all right, in order for this method to work. So that, of course, would just be 320 degrees. So hopefully this isn't difficult trig for you at this point, but if I wanted to find the magnitude of dx, I would simply use hypotenuse times the cosine of the angle. Notice I'm using the 320. That works out to be to 3 sig fig, 76.6 meters. Positive. Notice it's pointing to the right. We're in the 4th quadrant where x's are positive. On the other hand, to find dy, which is the side opposite the angle, we would use the sine function. Will it be positive or negative? Yes, it will be negative 64.3 meters. Negative because this vector is down. We're in the 4th quadrant where y's are negative. And if we use 320 degrees, right, the calculator will spit it out. Now, last year, this is where we would have left it. We would have said, okay, here are our perpendicular components for our 100 meters at 40.0 degrees south of east. But now, we can put it in unit vector notation. So remember that x in a direction is I cap, and y with direction in unit vector notation is j cap. And in this case, we have no k cap because there is no in and out of the board. So we could write this like that. Notice how I've grouped things, right? The units here on the 76.6, right, go with the number, right? They're part of the coefficient. They're part of the scalar component. And then the parentheses and I cap, then minus 64.3 meters. Again, that goes together in parentheses, j cap. You got to have units, right? Otherwise, you can't tell what it is that you're measuring or what kind of vector it is. Okay, that it's a displacement vector. And the I cap and the j cap, remember, are the directions. Note this minus here can go here, or it can go in with the coefficient, if you wish, with the scalar component. Either way, it's really meaning a negative j cap. A negative j cap is down. Right? So we're going to the right, and then we're going down by looking at the unit vector notation. And of course, hopefully you could do the opposite thing here, right? You could take this vector in unit vector notation, draw out the two components, draw the resultant, and then do a Pythagorean theorem and an inverse tangent to figure out the magnitude and direction. And so you need to be able to go back and forth. So you'll practice that. So I hope you enjoyed this little introduction to unit vector notation, okay, which is really going to become important when we start doing some more stuff in more than 2 dimensions, and in particular when we do vector multiplication.